All right, let's try to keep part 3 and part 4 rolling. I hope you did. I did such a good job of explaining that last problem that you guys were able to take good notes. But if not, here we go. Here's our next example, okay, class? And we'll do the integral test for this bad boy, okay? Or I'm sorry, the limit comparison test. All right, so here we go. If I did the nth term test, I would get 0, so I got to try something else. This kind of looks like a 1 over n squared. Like maybe I could compare it to 1 over n squared, but I couldn't use direct, right? Because then developing some type of inequality for that guy would be a little bit too difficult. So let's try this limit comparison test thing, okay? And I'm going to go ahead and get my sentence started, right? Since the series n equals 1 to infinity, I'm going to compare this to 1 over n squared. Why? Because it kind of looks like it, right? And I know that 1 over n squared, that dude converges. Right? How do I know that converges? Well, it converges by the p-series test. We've actually been using that quite a bit in our class. I should make sure it's writing. Oh, and it is sweetie sweets. Okay, so it converges by the p-series test. Now, I can't do the inequality, so I've got to do that limit thing. Okay, so and let's do the limit as n approaches infinity. And remember, when I set up this ratio, it doesn't matter what goes in the numerator. It does not go in the denominator. I know one thing for sure, that I'm going to want to multiply by the reciprocal. And if I do, if you're going to notice, I kind of get like my n behavior model, right? When dealing with limits. Well, we kind of started AP Calc with at the beginning of the year. Whoops, it's just b over n squared. And I get an answer of 3. How about it when 3 is finite and positive, right? And since it's finite and positive, okay, we know that my original problem, which I was trying to do, which is the series from 1 to infinity of 1 over this craziness, right? I know that bad boy right there converges, right, as well by what? Say it with me, LCT, right? By the LCT. And sweet, like when the marker doesn't work, it just doesn't work. And so I've got to, you're testing me right here. LCT. All right, let's see how it works if I just write the whole next one on here. All right, class, and you let me know in class if this was not a good idea. Booyah! This one's a little bit different, and I had somebody in class this morning say beautifully, they're like, well, let's just compare that to n to the 4th over n to the 5th. Well, what's n to the 4th over n to the 5th? Well, that's just 1 over n. So let's go since the series from n equals 1 to infinity of 1 over n, and that diverges, right? That's the harmonic p-series by the p-series test, Okay, and remember, I can't do an inequality, but I need something else. If I can't do an inequality, that looks kind of difficult if I'm trying to compare an inequality, so let's use this limit comparison test. The limit as n approaches infinity, remember, it doesn't matter what goes in the numerator, okay? Doesn't matter which one goes in the denominator, but the one thing we want to be aware of, there's no way I want to do that crazy division, so I'm going to multiply by the reciprocal, okay, which would be, what would that be? If I multiplied, I'm going to just go ahead and multiply it all and distribute, okay? That I get on top there, and then I get, sorry about that, I get n times that stuff in the bottom, which would be, oh snap, sweet, those match up. And since those match up, it's an n behavior model, which is faux, right? Which is finite and positive. We know that, and I'm running out of space. I apologize. I'll make sure I get a new page up here. We know that the original problem, n equals 1 to infinity. I apologize. N to the 4th plus 10 over 4n to the 5th minus n to the 3rd plus 7 diverges as well by the LCT. Kind of fit it in even on my face. Oh, darn it. Try to write on my face. Okay, see you in a moment. Aloha, class. All right, I think I got my situation figured out, so let's go. These kind of get repetitive. I'm not going to do this one, okay, but you should do it on your own. You should compare it to that guy right there. Okay, and it kind of looks like a direct comparison, but if you notice, the inequality wouldn't work out for that, and that's why we need a limit comparison for that guy. Now, I wonder how many of you would have thought about this guy, right? Okay, what are you going to compare that to? I know what I'm going to compare it to. It looks awfully similar to 1 over the square root of n. And 1 over the square root of n, it would be 1 over n to the 1/2. And we know that that dude right there diverges. Oh, snappity-dappity-dappity. I almost thought I made a boo-boo, but that dude definitely diverges because your p is 1/2, your 1/2 is smaller than 1, and that diverges by the p-series test. Okay? Now, I can't do an inequality for that. That'd be a little bit confusing, right? And so let's just do the limit comparison test. Now, how the heck do I do it for this little square root dude? Well, let's see. We have 1 over the square root of n over 1 over the square root of 3n minus 2. Okay, we don't want to divide by a ratio or a fraction, so let's multiply by the reciprocal. Okay, and that's kind of end behavior model, right, class? That's just going to be equal to the square root of 3 over 1, square root of 1, which would be the square root of 3, which is, right, finite and positive. And because of all that stuff, we know that the original problem that looks pretty tough off the bat, right, of 1 over the square root of 3n minus 2 diverges, right, as well by the LCC, the limit comparison test. All right, we're going to keep moving. Okay, I know there's a lot to take in right now. Okay, you're going to have a big time homework assignment that you want to make sure you are able to do. Okay, but we're going to go to what is called a alternating series. And what the heck is an alternating series? Well, it is a series that alternates between negative and positive terms in the sequence. Usually, an alternating series is a dead giveaway by having something like a -1 to the n, a -1 to the n plus 1. You could even do a -1 to the n minus 1. You kind of get the point, right? It's going to have something that is going to alternate our terms between a negative and a positive, right? The hidden alternator, well, think about it. There's a hidden one. We actually kind of looked at one of those problems today that actually is an alternator, and if you're not very careful, you're not going to be aware that it's an alternator. It's alkaline water, yum yum in the tongue. All right, here we go. Alternating series test. It's kind of a nice one. When you see that you have an alternator, okay, which is of these two formats, generally in AP Calc, we say that this is a one-way test. We've been doing a lot of two-way tests, and a two-way test just will help us determine whether something converges or diverges, okay? A one-way test only tells us one thing. So for an alternating series test, a one-way test will tell us whether it converges. It won't even tell us if it diverges, okay? That's if we are using this test. And all it has to do is have two things come true. Okay, which are these two things? We need the limit of, take out the alternator, and we need the limit to be equal to 0, and then take out the alternator. That sequence needs to be decreasing. It needs to be a decreasing sequence. It doesn't mean, sometimes we'll deal with sequences, and they may increase. It might go 6, 8, 10, 7, 6, 5, 4, 3, 2, 1, 1/2, 1/3. As long as it decreases for the long haul, that's considered a decreasing sequence, okay? All right, here we go. Let's get after this, do some of these guys, and you know what? It's going to make a lot more sense when we attack these. Oh, not much space there, right, class? No way, Jose. And it's because there's not a ton of work that you have to show for these guys. All right, but I'm going to give myself a nice big page here, okay? And let's do this first one here. We have the series n equals 1 to infinity of -1 to the n plus 1. Oh, snap, that is an alternator. Okay, so my first step is since. Okay, step 1, let's see if that guy comes true. Take out the alternator, and let's do the limit. That's n over 2n minus 1. Ooh, that equals 1/2, which is not equal to 0. So that dude diverges by the nth term test. Nth term test. Okay, that still holds true with this stuff, all right? So how about that one? All right, let's roll. That dude's done, so, right? We didn't even have to use the alternating series test to do that, all right? Let's do this next one. I'm going to help you out. Next one, nth term test. Boom, works out. Does not equal 0. It actually equals infinity. So that dude diverges by the nth term test. All right, let's go to our next one. And this is our secret one because we're going to let n equals 1 to infinity. Remember, those are counting numbers. So that means we're going to put a 1, a 2, a 3, all those guys in front. And if you notice, it's cosine of pi, right? But it's going to be 1 pi, 2 pi, 3 pi. So believe it or not, that dude's an alternator. So we're going to go since since it's an alternating series, I'm going to throw out the alternator and I'm going to do step 1, which is check out the limit as we approach infinity of the alternator out of there. Okay, and I get 1 over n. And what does 1 over n do? Oh, that equals 0. So that's check number 2. So since that checks out, and 2, 99.9% of the time, whenever we're doing an alternating series, that sequence will be a decreasing sequence. And believe it or not, that's 1 over n. So it'd be 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. It's definitely decreasing. Okay, and since, I talked so funny, it stopped the pen. Okay, so a sub n is decreasing. So is a decreasing sequence. Okay, is a decreasing sequence. So we said the 2 important things. Oh, now all I have to say, we know that the original problem, n equals 1 to infinity of cosine n pi over n. This is just converging, right? So if it's 1 and 2 good, then we know it converges. And this is not like as well, right? We're not comparing this to anything. We just say it converges by the AST, the alternating series test. That's it. Okay, let's keep going. I really don't want to get a new page out. So I'm going to try to do this guy. I apologize if you don't like it. Too bad. So sad. Actually, no. Okay, I got us a new screen here. I know I write a little bit better on this big guy here. So let's go, okay? It's kind of rapid fire these guys, all right? The sum, the series, n equals 1 to infinity. Negative 1 to the n minus 1. Snap, that is an alternator over 1n factorial. So I go since, right? There's 2 things I have to check. Number 1, the limit. Let's take that alternator out of there. 1 over n factorial. That is equal to 0. Check. And 2 is a sub n, which is equal to 1 over n factorial. Yes, is a decreasing sequence. Okay, so I'm check 1, check 2. Sounds like you can make a rap song out of that bad boy. Check 1, check 2. Okay, since those 2 things work out, we know that the series n equals 1 to infinity of negative 1, right? I'm going to put this guy in here. We know that dude converges, right? This is a one-way test. Converges by the AST, by the alternating series test. And that's it. That's all you got to do. How about it? So it's not too bad, right? It's kind of nice when we do some difficult stuff and we come back here and we do a little bit of nicer stuff. All right, let's look at this next dude. Okay, here we go. The series n equals 1 to infinity. Negative 1 to the n. That's another alternator over n minus 5 squared plus 1. Well, since it's an alternating series test, let's just start writing out my little saying. Well, I need 2 things to happen for this one, right? I first need the limit as I take out the alternator, and I need that to equal 0. Oh, sweet, it does check 1. And then check 2. I just need this guy right here, once again, without the alternating, to be a decreasing sequence. And you know what it is? If you don't believe me, write out some terms. I actually think this increases a little bit, but it decreases forever and ever as we get really along the sequence. It's a decreasing sequence. We know that, right? That's it. We know that my original problem, which was the sum as n equals 1 goes to infinity, that alternator's got to be in it in this conclusion, remember, n minus 5 squared plus 1 converges. Remember, this is not it's not a comparison, so it's not as well or 2, but it converges by what? By the AST. And write those out by the alternating series test. Okay, here we go. Our last one. I think it's a piece of cake. You're going to do it on your own. All right, next. I'm going to go straight to 17. I know you got your notes in there. Where are our notes? Okay, we did this guy. Let's get these notes up here a little bit. It's called what we call absolute versus conditional convergence. Okay, and I think the best way to kind of give us a good explanation of what's going on, it kind of says it right here, you guys. It's conditionally convergent if the series converges, but the absolute value of it does not. Okay, what the heck does that mean? Well, what that means is, well, you know what? Let's do some work. Okay, it's helpful to do the work on these problems, and I'm going to help you out. Okay, let's go ahead and do these next 2 together. Okay, what I want to determine right now is if the alternator is a major difference in what is going on. What do I mean by if the alternator has a major difference? Well, let's go ahead and do this one. Okay, Let's pretend it's like an ACT. You know, like AST. Okay, it would be awesome. You hit pause right now and do the AST on this guy, right? It's got the alternator. So we're going to go since. Okay, since 1, all I need is 2 things to work out, right? And goes to infinity. I almost in my head, that's why I started. I was like, oh, I could just compare this. Can't compare, it's got the alternator in it, right? So all I have to do here is just do this guy, right? That's equal to 0. Check 1. Okay, and then 2 is 1 over the square root of n decreasing. For sure it is. It's definitely a decreasing sequence. Whoops, decreasing sequence. Check 1, check 2. Right? Okay, then we know that. My original problem with the alternator in there. Okay, with the alternator. Whoops, what the heck are you doing? Where n equals 1 to infinity of -1 to the n over the square root of n. This dude converges. You know, it's interesting though. And that converges by the AST. Now check this out. Check out this fancy word. Furthermore. So whenever the APA asks me, is this conditionally convergent or absolutely convergent? I have to write a little furthermore. Okay, so here we go. Furthermore. Since. Let's talk about this series without the alternator. What does that guy do? That guy diverges. Like that guy diverges, right, by the p-series test, right? That guy diverges by the p-series test. And since, okay, let's think about this. Let's think about this for a brief moment, okay? This actually, with the alternator, converged, right, by the alternating series test. However, if I totally throw that alternator out and just do the series without the alternator and it diverges, then we say that this problem right here, because of all of this beautiful written explanation, that this is conditionally convergent. Okay? Because it does convergent, but it's conditional on that alternator. If it doesn't have the alternator, it actually would diverge. And if you think about this, 1 over the square root of n, that's going to diverge. But when I throw the alternator in there, right, it's going to go from positive to negative, so it doesn't go as fast, and that's why it converges. You're probably saying, how could that happen? Well, I just told you. All right, here we go. We got to keep going. I think I got a couple more tests after this, and we're going to get them all in. We're going to fight it. All right, here we go. My next one. N equals 1 to infinity, right? And the AP is getting specific on this one. They're going to ask me if it does converge to specify if it's absolute convergence or conditionally convergent. All right, so let's check this guy out first. It's got an alternator, so I know I'm going to use the alternating series test. So since I've got to check 2 things first to see if it converges. First, the limit without the alternator, is it equal to 0 to 1, right? And then 2, is my sequence a decreasing sequence? And for sure it is. Check 1, check 2. All right, we know that. Okay. So that means we know that my original problem, which is n equals 1 to infinity with the alternator in it, that this dude is going to converge. How do I know it's going to converge? Well, I know it's going to converge by the alternating series test, right? I satisfy check 1, check 2. Furthermore, right? Oh, snap. Oh, phew. Furthermore. Okay, what can we talk about? Furthermore. All right, let's throw that alternator totally out, and let's see if it's conditional or it's absolute. Well, if I throw the alternator out, I get 1 over 3 to the n, which is technically 1 over... Oh, but that converges, right? That converges. How do we know that converges? Well, it converges by the GST. Well, it converges with or without the alternator. Well, if it converges with or without the alternator, we call it absolutely convergent. Okay? Because it doesn't matter if I have the alternator or not the alternator. That is absolutely or absolute convergent. How about it? Not bad, right? Not bad. I know it. I'm with you. We're throwing a ton your way, and it's so awesome that we're in BC because you guys are so smart. It's cray. Let's keep going. We're going to do the remainder. In class, I want to get these last 2 tests down. Okay, we have what we call the ratio and the root test, and they're somewhat a little similar, okay? But here we go. What's the ratio test says? Well, if we have some series, okay, of non-zero terms, okay, then that series will converge if this is true, if that limit is true. Okay, it will diverge if this limit is true, and it will be what we call inconclusive if your limit is equal to 1. Okay? So go ahead and keep that up. I know it's nice for you guys, you have that, but I'm going to go ahead and use my bigger page here, okay, my blank page, so I can go ahead and show all the good work of using. We got 2 to go. Right, let's get these 2 examples done, okay? Here's A. The sum n equals 1 to infinity of 2 to the n over n factorial. Well, this doesn't look like a p-series, doesn't look like geometric, it looks crazy, right? What the heck am I supposed to compare this to? Woo! Well, whenever I have factorials and an n up there, kind of like a geometric series, but it's a geometric series with a factorial, then that means I want to use the ratio test. Well, how the heck do I do a ratio test? Well, it's a limit. It's a limit of the absolute value of a to the n plus 1. Well, what the heck is a to the n plus 1? Well, that just means I'm going to put an n plus 1 wherever I see an n. Okay? And I'm going to divide that by a sub n. That's what that little formula says. Now, we all know we don't want to divide by that crazy fraction. So instead of dividing by that crazy fraction, we are now, if you notice, it's infinity over infinity, right? So I got to try something else, which I'm going to simplify. Okay? And as I simplify, I'm going to write that's 2 to the n times 2 to the first over, I'm going to write n plus 1 factorial as n plus 1 times n factorial, right? It's another way to write that, right? We just keep on taking away 1. Yes, yes. All right, and then I'm going to, instead of dividing, I'm going to multiply that by n factorial over 2 to the n. Now, if you notice, I already simplified because I knew that shling, 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 shling. Oh, sweet. So all that stuff went away. So then what do I end up with? The absolute value of n over n plus 1. Well, that is equal to 0. 0 is less than 1. So then that means this dude, what does it do? Let's look at those handy dandy notes. Oh, that converges. Okay, so it means it converges by the ratio test. Okay, that's it. And then your original problem does. Kind of okay? All right. B's kind of tougher. So challenge yourself, please. Learn more. Okay? Hit pause and see if you can do C. Okay, hit pause. See if you can do C. All right. Hopefully you tried it on your own. Okay, you will learn a ton more. But if you didn't because you were weak sauce, here we go. Well, once again, I mean, it's got that factorial. It's got to the end. That's going to mean the ratio test, all right? So here we go. It says infinity. We do the absolute value. I plug in an n plus 1. So that's going to give me an n plus 2 factorial over 3 to the n plus 1. I'm going to divide that by a to the n, which is the original problem. Okay? And once again, I'm going to do some simplification here as we go. Okay, as I flip it. But n plus 2 factorial, I could write as n plus 2 times n plus 1 factorial. And I'm going to stop there because I notice that it's going to cancel out. And then 3 to the n plus 1 would be 3 to the n times 3 to the first. Multiplied by, there it is, zip it go. And I get this bad boy. Oh, sweet, sweet. Schling, 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 schling. And I get equals the limit as n approaches infinity of n plus 2 absolute value over 3, which would be equal to infinity, which is greater than 1, which means it diverges by the ratio test. Right? That means this guy, the original problem, diverges by the ratio test. Okay? So hopefully you tried that one on your own. We got one more to go and then one more test. Here we go. Okay? The sum n equals 1 to infinity, right, of n squared. This one's kind of funky. It's got a whole bunch of stuff in it. B plus 1 over, challenge yourself. Do work. Okay, that's craziness. It's got that no factorial, but a whole bunch of exponents and stuff like that. I don't know what the heck you're going to compare that to. So that might mean ratio test. That'd be n plus 1 squared. Right? That'd be 3 to the n plus 2. That'd be all over 2 to the n plus 1. That's craziness. All over the original. Okay, right? Which that's just nutty. So let's go ahead and see what we can simplify here. n plus, oh, sweet, of course, because I'm almost done. Okay, so n plus 1 squared, that's going to stay as it is. That can be 3 to the n times 3 squared, right, class? 3 squared, all over 2 to the n times 2 to the first. And then I'm going to go a little reciprocal, and I get n squared, and then I get 3 to the n, 3 to the n, and 3. So the 3 to the n, shling, 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 and I get equals the limit as n approaches infinity. Hopefully I don't get lost here. Absolute value of, there's a niner up there, right? N plus 1 squared all over, am I a 2, a 3? That's a 6n squared. Oh, that's n behavior model. That's the same. That's going to be 9, 6, which is 3 halves, which is bigger than 1, which means it diverges, right, by the ratio test, right? Because if that's bigger than 1, it says it diverges by the ratio test. Okay. It looks like I got to do one more. Okay, so we got one last test. Let's do work. Let's get it done. Okay, here it is, the root test. Now, when the heck do we use the root test? When you use the root test, your series is going to converge whenever the limit, and you take the nth root of it, is less than 1. It's going to diverge. You take a limit in the nth root whenever it's greater than 1. And it's inconclusive when you take the nth root and it is equal to 1. I think I might be able to fit all this in here. Let's check it out. All right, so first and foremost, when the heck would you ever use a root test? Because that might look like you could use a ratio test. Well, whenever you can write your series, as something to the n power, you want to use the root test. I'm going to show you why. Boom, I was able to write it to the n power. So now all I have to do is do the limit as n approaches infinity, and I'm going to take the nth root of my sequence. Okay, what happens to those? Power, root are the same, they go away, so then I do my limit, okay, infinity, e squared over n. What would that be equal to? That would be equal to 0. Well, 0 is less than 1, and since it's less than 1, we say it converges by the root test. Boom, not bad, right? Check out the next one. Okay, check out the next one. Can you write the next one as something to the n power? Oh, sweetie, sweet. It already is. So then I just got to go to limit as n approaches infinity. Take the nth root of all that stuff. Okay, whatever you say. Shling, shling, right? The root and the power cancel themselves out, and I get 3n plus 4 over 2 to the n. Oh, snap, that's n behavior model, which is 3 over 2. 3 over 2 is bigger than 1. Shling, shling. It diverges. How do we know it diverges? We say, oh, sweet, the pen man. Oh, sweet. We say it diverges. How about that? Came back to life. By the root test. Okay, oh my gosh. Oh my gosh. That was craziness. If you wanted a big time challenge, example 22 has those problems all mixed up. And believe it or not, sometimes you can use multiple tests or different tests. Remember to always get started with the nth root test, right? I'm sorry, the nth term test. Because if the nth term test does not equal 0, you know that dude diverges and you're done. I mean, look, there's probably about 3 or 4 of these you could get done right there by doing the nth term test. And then remember, we got geometric series test, we got p-series test, we got alternating series test, we got a direct comparison test, we got a limit comparison test, we got I already said alternating series, we got a ratio and a root test. You need to know all of them. Good luck. Come in for help. Aloha.